MTL thing. So we are supposed to upload here. And anyway, everything you will find in that our MS team as well. But remember that here also you will find that one. But I don't know this recorded video will stay here or it will be deleted. I'm not sure about that. It may be deleted after few days. I'm not sure about that. But anyway, even if it is deleted from here and also it is not um, so if you go from here, then you can find actually. So there is a pattern, right? So lecture 1, lecture 2, lecture 3, and here it will be tutorial 1. So there will be a pattern here. So it is easy to find. Maybe before exams, you can go through this importance where you can find all the lecture notes together and all the videos together. It is better actually, because if you go through only that MS team, then I upload here every week, but there is no pattern, right? And also that lecture notes and videos, these are in the different places. So maybe it is difficult to find. Okay. So here I start today's lecture, and also I will upload this lecture notes also today after the lectures only. So today we will discuss ordered topology. So anyway, so if you have
Sir,
any, yeah.
sir, can you explain subbasis once again, sir?
Sorry, one.
Subbasis, sir. How subbasis and basis are different?
Okay, good. So whenever you have questions, you should ask. Otherwise, I do not know who have problem or not. Now, first of all, what is a subbasis? Now, suppose X is a topological space and say S is a collection of say A alpha, where A alpha, say alpha belongs to some index set, this one, and A alpha subset of X. And also it has property that if you take union over all of this one, A alpha, then you will get the whole space X. Now, if a set of collections of subsets satisfies this property, then we will call it is a subbasis. That's all. Okay. It is a subbasis for a topology. But for which topology, we do not know yet. Now, obviously, now if you take that elements of that subbasis, then obviously it does not form a basis. Now from the subbasis, now we can make a basis. How to generate a basis? Now we take B as all the finite one, that is all A1 intersection A2 up to AN, where this N is a, or we can say just N belongs to natural number, this kind of collections, all of them, this, and AI belongs to this set S. Okay, so that's mean now if we take any elements, any finite collection of elements from S, and if we take the intersection, then the new collection, this one, forms a basis. We check that in the last lecture we have checked that, then beta forms a basis. Now this is called that S generates B, or you can say that beta is generated by S. Okay, now you can, now if we take n elements, say A belongs to S. Now obviously A can be treated as intersection of itself, so therefore A belongs to beta as well. So that's mean S subset of beta. But if you take an element of beta, it may not be a subset of S, right?
Sir, can you repeat this?
Sir,
How A is contained in beta?
Because A is a, take an element A belongs to S, right? Now what is A? Now what is actually beta? Beta is a collection of all of the finite intersections, where n belongs to natural number. Now suppose your n equal to 1. That's mean what is what do
Oh,
you mean n equal to 1? So that's mean all the only single element, that is a1, that is also you can take, we are talking about a finite intersection only, right? So that's mean if you take only n equal to 1, then it will be a1. Now that's mean beta contains all the elements of s as well.
okay, sir. Got it. Thank you.
Okay, so that's mean you can take beta, right? Okay, so any other question, or is it clear?
Sir,
Hmm.
do we have a restriction on the lower limit of cardinality of a basis? Like, how low can we go for the cardinality of a basis? Do we have a
No, no,
restriction on that?
no. We do not have any restriction.
Like, suppose if the topology has infinite number of elements,
Hmm.
we cannot get a finite basis, right?
No, we
Because they're
cannot get,
unique.
right.
So,
Be, huh.
so do we have like such kind of any characterization? Suppose the topology has 2 raised to power r elements.
Right.
So do I have a restriction on the cardinality of the basis, like how low I can go? Can I
No,
have a
there
countable
is
basis?
uh, right. You cannot say actually. So you have countable basis or not. You may have countable basis or you may not have. It depends on the depends on the topology on that space. It
Okay,
cannot be
sir.
said that it is either countable or do you have a countable basis or not. It is not. You cannot say that.
Okay, sir.
For an example, see what is actually a basis. So whenever you have a basis, so that's mean it is all possible union of the elements, right?
Yes.
So that's mean if it is only sure that if you have a if you have a say finite basis, now if you take all possible union of the finite elements, then you should have finite elements only. So that's mean
Yes,
that
sir.
the topology generated by that basis should be finite. That is fine. Now, but if you have a basis which is suppose countable,
Yes,
and now
sir.
we are taking all possible unions, right? Now all possible unions may be countable or may not be. That's mean it
Uh,
depends generally,
no, sir. No,
right?
sir.
It is uncountable generally, right? Because it is all
What
possible
what
union.
what I am trying to say is,
That reverse. I
I can get the uncountable thing, like,
right. I
but
understand your point. So if you have a say uncountable number of open sets are there, so can you always have a countable basis, right?
no, no, sir.
Hmm.
That is not my question. My
Okay.
question is, suppose I have a countable basis,
Hmm.
and I can distinguish between different kind of uncountable sets, right? R, 2 raised to power R, 2 raised to
Right.
power 2
Right.
raised to
It
power
depends
R.
on.
So, given a countable basis, what is the maximum number of elements in the topology?
Right. So that's why I'm saying. So whenever you have a countable basis,
Yes,
suppose you have
sir.
a countable basis, now you are taking all possible unions. That's mean that cardinality of your topology will be that cardinality of continuum. That is only C.
Okay, sir.
It is
So I
not the 2
cannot
to the
exceed
power r,
C, right?
the
I
number of
cannot,
the open sets.
yes, sir. I cannot exceed C, right? That's what my
No,
question was.
no, I think.
Okay, sir. Okay.
And similarly, if you have um, uh, only that say cardinality of R, if you have the number of open sets, that one only, and if you are taking all possible unions, right? I do not think it will exceed that one as well. Right? It will not exceed, right? Because ultimately, what you have uh,
A subset of the power set of that set.
uh,
So, I cannot exceed like 2 raised to power that cardinality of the
Hmm,
basis, right?
that is fine, right?
Okay, that was my doubt.
Hmm.
Thank you, sir.
Okay, so do you have any other question from the from the last lecture? Okay, so now we define order topology. Now, first of all, so let X be an ordered set, or you can say that be a set with an order. Say this. That's mean you can define a order on X. Okay, and here a simply order means we just can compare two elements. That's mean if you have any two elements from X, that's mean you can only say that either A is less than B or B is less than A, or they are equal or not. Okay, so we just order this one. Now then we define some intervals in this way. So whenever you have AB, okay, so that's mean all the elements of X such that A less than equal to less than X less than B. Okay, and here AB belongs to X. And if we have AB, so that's mean you know that definition. So A less than equal to X less than B. Similarly, we can define A, B, and that closed AB. Right? We can define in this way. Now, for a set X with just we can say order relation, this now let beta be the collection of open sets. Okay, collection of intervals. This one, first of all the intervals open AB. So this one, all of this type of interval where A comma B belongs to X. Okay, let beta be the collection of all of this. Secondly, let all the intervals A0 comma B here closed A0, where A0 is the smallest element of X. Okay, and so third property is that collection is all the intervals say A comma B0, where B0 is the maximum elements of X, right? And then it is easy to check that beta forms a basis. Now then beta forms a basis. Now the topology is topology generated by beta is called the hmm, ordered topology on the set X. Now example, now suppose your X is R. Okay, now suppose your X is R and you define this order, then which topology you will get? What is the order topology on R?
Usual topology.
Yes. topology on R is same as usual topology on R. And which type of open set basis element it will have? We have 1, 2, 3. Which type of it have?
Open intervals,
Okay. And 2
finite
and
open
3?
intervals.
And 2 and 3?
Uh, a comma minus infinity comma a comma infinity.
No, no, that is fine. I am saying that this type of interval it will have.
No, sir,
Why?
because there are no maximum in R.
Right. So here you should write if exist. Right? We do not know that elements will exist or not. It is that's mean it is just usual topology on R, right? Now tell me if x equal to natural number, then what will be that order topology on R? Tell me.
Discrete topology.
Yes. So it is same as discrete topology. Okay. Now tell me why 2 is open, singleton 2. Why singleton 2 is open?
1, 3, open interval is
Right.
2.
So 2 means actually when my x is n, then 2 is my open interval 2, 3. And why 1 is open?
Of second form closed 1 comma 2 we take.
Right. Now that will be closed 1, open 2. Because it has the smallest element and that is 1. Right? So this 2. So that's mean every singleton set is an open set. So therefore, usual order topology on N is actually a discrete topology. Is that clear? Now tell me, this is a little bit, say 1, 2 cross N. So that's mean this in this way. It is going. So it is 1 cross 1, 1 cross 2, 1 cross 3, 1 cross 4, and then 2 cross 1, 2 cross 2, 2 cross 3, 2 cross 4, and so on. Now tell me, now this is your X. Now, what is the order topology on this topological space?
So what is order relation?
Good, I did not define that. Good point. So, for to order set X and Y, we define, it is called dictionary order. Dictionary order on X cross Y. In the sense that, that's mean, say A cross B, we take element of X cross Y as A cross B, okay? That's mean we call that X cross A cross B belongs to X cross Y. That's mean A belongs to X and B belongs to Y. Okay. Now X cross B less than C cross D, we define in this way, either A less than C or A equal to C and B less than D. So that's mean it is called dictionary order because we first compare first two terms, say A and C. Now if A is less than C, then we call that A cross B less than C cross D. Okay. And if the first term equal first two terms, then we move to the second term. That second term are equal or not. Okay. So this is called dictionary topology. Why dictionary topology? This order generally follows in the dictionary. If you look at the dictionary, right? So that's mean if we take say 1 cross say 5 and say 2 cross 3, tell me which one is bigger?
2 cross 3.
This is bigger. Now if we take 1 cross 7 and say 1 cross 5, then which one is bigger? 1 cross 7, right? Okay. Now tell me. Now we have this dictionary order topology and we have this set. Now what kind of order topology it is? Can you say it is a dictionary order topology? Means
Again, discrete.
sorry, again discrete. So why this is discrete?
Singleton set is open.
Right. So what is my 1 cross 1? That's singleton. What is my 1 cross 1?
1 cross -1, comma 1 cross 2.
1 cross -1. Minus is not here. What is -1?
1
1
cross
cross 1
1
comes from the
goes
second property.
second property.
That
Yes.
is 1 cross 1, comma 1 cross 2. This was. Now what is my 1 cross 2?
Open interval 1 cross 1 comma 1 cross 3.
Good. Now what is my 2 cross 1?
Second
think
property 2 cross 1, comma 2 cross 2 open.
But 2 cross 1 is not a list element.
1 cross 1, 3 cross 1.
it's not open.
It is not open.
Sir, we can take intersection. Then can we get this 2 cross 1?
No, you cannot get 2 cross 1, right? You cannot
Okay.
start with 2 cross 1. If you cannot choose closed interval because it is not a list element.
No, sir, I was talking about intersection. Can we take intersection to get 2 cross 1?
You can get intersection, but first of all, what are the open sets here? So intersection.
I will take open interval 1 cross n
1 cross.
n for any natural number.
Okay, you can take 1 cross 10.
Then 2 cross 2.
2 cross 2.
And okay, in this case, I'll have to take infinite intersection, which is not allowed. Sorry.
So this is not open. Is not open. Okay. So here all the singleton sets are open except this one. So therefore this is not the discrete topology.
Sir, can you explain this again?
Right? Because if A cross B less than 2 cross 1, then since this is already lowest one, so therefore then A less than 2. Right? So thus or you can say that imply A equal to 1. Any open set containing 2 cross 1 is of the form 1 cross n, comma 2 cross m, where n is any natural number and m is bigger equal to 2. So thus this set must contain 1 cross n plus 1, 1 cross n plus 2, everything. So therefore, thus that singleton one, the 2 cross 1, that one is not open. Okay. So any doubt?
सर हम ऐसा बोल सकते हैं क्या एनी फाइनाइट सेट कंटेनिंग 2 क्रॉस 1 इज नॉट ओपन.
गुड. हाँ हम ये भी बोल सकते हैं. नहीं, हाँ एक मिनट. हाँ ये भी बोल सकते हैं. Because if you take any open set containing this, that should be open. That should be infinite. So any open set containing 2 cross 1 is infinite. So that's mean in other words your statement is correct. So any finite set containing 2 cross 1 is not open. Okay, okay, done. This one. Fine. Now I will come to back to this question again. That is this problem again. That dictionary order topology. Okay. Now this way we can define order topology. So now note that. See, you know, right? As a order, we know that complex number is not a ordered set, right? You know that. See, R has a order, but complex number does not have any order. But here you can give a dictionary order in set of complex number as well. And also you can generate a dictionary order topology there in C. But note that with that topology, that is dictionary order topology, that topology is different from the usual topology on C. Okay, we shall see this later. Now move to the another type of topology that is called product topology. So let x tau, say tau x, and say y tau y be to topological space. Okay.
Sir.
Hmm.
So in the previous example, we can define it order in some other sense, or that topology will be discrete topology.
Sorry, I did not get your question. What?
Like we can define the order in a different sense. Like we can go smallest element to be 1 cross 1, then 2 cross 1, then we go 1 cross 2, and then 2.
Right.
So, sir, my question is, so you said the normal order topology on complex number is not equal to the usual topology. So, is
No,
that
not normal. I said that dictionary order topology.
okay? So can we define any order topology that will be equal to the usual topology?
In C?
Yes, sir.
No, that is not possible.
can we prove that?
Yeah, there is a proof, but currently I do not remember the proof, but one can prove that. That is not ordered.
Okay.
That is even R2, that is R cross R is not ordered. Okay, now here suppose you have X tau is a topological space and Y tau is a topological space. That's mean X is a set and tau is a collection of open sets of X, right? And here also Y is a topological space and what is tau? Tau is a collection of open sets, or you can say open subsets of Y. Okay. Now if you take that collection, say U cross V such that U belongs to tau X and V belongs to tau Y. If you take that collection, now can you say that that collection is also forms a topology?
So I think it will be a basis or some sub-basis.
No, what is my question? That is a different thing. I am asking that can you say that this forms a topology? Yes or no?
No, no.
No,
No.
sir.
Can you give one example where it does not form a basis? Even pictorially prove. If you can give a pictorial example, then also it is fine.
Sir, the union of two, like the union of U1
Right.
cross V1 may not be a union of the product.
Exactly. Because if we take say this one, say in R2, if we take this and say if we take another one, this, right? So their union will be this set, right? So if you take say U1 union U2, sorry, U1 product V1 union U2 product V2. Now this cannot be equal to some U3 cross V3. That is generally that is not equal. Because if you take this kind of open set and this kind of open set, in general, it can be equal, but in general, this is not equal. Or you can say always no. You can say this and this may not be equal. May not be equal, right? Because if you take this kind of set and this kind of set, if you take their union, see their union cannot be written as this form, because this form means should be a rectangle. Okay, so therefore only this collection does not forms a topology. But again, can this collection forms a basis? Yes. Yes or no? Is this form a basis?
Yes, yes.
Yes. Why? Because if you take their intersection actually, then their intersection is this one. Now that one can be written as their intersection. So now we call this. Now beta forms a basis as if we take U1 cross V1 intersection U2 cross V2 equal to U1 intersection U2 cross V1 intersection V2. Right? So the second property of basis satisfies and first property is trivially satisfied. So therefore beta forms a basis. Okay. Now the topology generated by this beta is called product topology. Product topology on the x cross y, because this is subset of x cross y. Okay, now do you understand what is the product topology? Okay, now this forms a basis. Now can you give me another basis which has less number of elements? Because this is looks like a huge class, right? We are taking all the open sets of x, all the open sets of y, and we are taking all possible product. So this sets is a huge one. Now can you give a smaller set which also forms a basis for the product topology? Any guess?
All product of
Take a
basically
product of
Right. Now if it has a basis, say beta 1, if it has a basis beta 2, now if you take u from beta 1 and v from beta 2, then this beta also forms a basis for the topology. Now but this is not a definition, right? Now definition is this one which I write in the red color, and which I write in the green color. You have to prove that. Now how to prove that? Now how to prove that theorem? So let beta 1 be a basis for a topology on x1 and beta 2 be a basis for a topology on x2. Then that collection, we can write a different name, say D, all the B1 cross B2 forms a basis of the product topology on x cross y. Right? Now tell me how to prove that. What is the procedure? So if I ask you to prove this, then how will you proceed? So you should know the proof, right? Tell me. Anyone? Yes.
so for any open set u cross v.
No, actually just tell me the rough idea. So that is fine. Actually what you need to do, how to start this kind of problem. That is how to start the solution.
Okay. I
Sir,
mean,
the first condition holds because for every point belonging to x cross y, we get an open. We have to get a set in b1 cross b2, right? So we have a set containing a comma b. From a I get a set from b1, and for b I get a set from b2. So for every point in x cross y, I get a
No.
set in b
Actually
cross.
you are in right track. That is fine. Actually I did not ask that one. So whenever you have this kind of problem, what you need to prove. See, now this is a basis. This basis forms a topology, right?
Yes,
And you
sir.
have the product topology, which has a basis. Now you have to show that both topology are same.
So we can start by showing that B1 cross B2 is an open set in the product topology and then use that lemma that we did
Right,
earlier.
right.
Yeah.
Exactly.
Oh,
So
okay, sir.
actually what you need to prove actually. So first of all, so let that this basis say generates say tau dash. Okay. And let tau be the product topology generated by my beta. What was the beta? It was U cross V, where U is open in X, V is open in Y. Okay, so you need to compare this. Now tau dash is generated by this, tau is generated by this basis, and you have to show that tau and tau dash both are equal. Okay, now note that here, see, since B1 from beta 1 and B2 from beta 2, so that implies B1 and beta 2 are open in X and Y respectively, because each basis elements are open, right? So therefore B1 cross B2, this is actually belongs to your beta as well, right? And this is subset of tau. So that's mean all the basis elements that's of tau dash are in tau. And what is this tau? Tau is the union of all those basis elements. So therefore tau dash is subset of tau. And the converse part is also simple. Now you need to prove that tau subset of tau dash. Now first of all, let take any basis element. Say W belongs to tau. So take any open set. We need to show that W belongs to tau dash. Okay. Or you can show that take a basis element here. Okay. Anyway, we can prove that one as well. This one. Now that imply first bracket definition for each say X belongs to W. So there exists U V beta U cross V in beta such that X belongs to so X cross Y. It is better. X cross Y belongs to U cross V subset of tau subset of W. Why? Because W is an open set and this is an element of that open set. So therefore you must have a basis element, right? That is the definition of basis. Now that implies X belongs to U and Y belongs to V, right? Now since X belongs to U and U is open set, so that implies there exists B1 belongs to beta 1 and B2 belongs to beta 2. That implies X belongs to B1 subset of U and Y belongs to B2 subset of V. That implies X cross Y belongs to B1 intersection B2 subset of U cross V, and which is W. So therefore you have an open set W, and if you take any element and you get a basis element from delta from D, right? So that implies W be a open set in tau dash. So we have the other possibility. So tau is subset of tau dash. So therefore tau
Sir,
is
it is
equal to tau dash. Sorry?
B1 cross B2, I think it's.
Ah, sorry. Right?
Yes, sir.
So,
So,
so like we defined the product topology. So we can extend this up to for finite cross product. Then
No, I did not get. What do you mean by finite cross product?
like I have n
Acha,
topology.
x1 plus x2 plus x3 in this way.
Yes, sir.
Ha. Tell me, yeah.
So does this hold for countable cross product type of thing? Like if I
That is a good question. That is a very good question. Now, what is your name? Who is asking that question?
so Shami.
Shammi. Okay. Now, this is a very good question. Now, he is asking that. Now, we define product topology on x1 cross x2, right? Similarly, we can define x1 cross x2 cross x3 as well. Similarly, we can define this cross x4. So therefore, we can define product topology x1 cross x2 cross x3 cross x4 as well, right? Now he's asking that what about the countable product? Now suppose my x is say x1 cross x2 cross x3 in this way. It is uncountable. Then how to define the product topology? There. Now there in this case we define that product. We define topology on X in two ways. One is product topology, another one is box topology. Now this is very important in other subject as well. And this is the general sense. And this is important only in topology. Only in this course. Okay. Now what is product topology actually? So I can explain you. So that's mean any how to find that any basis elements of this one will be of the form in this way. That is will be finite warp u1 plus u2 up to some finite, and then all the elements will be whole X. This way. So in this way you define the product topology. And box topology means you can take any arbitrary open set and you can take product. So did you get this too?
So can you explain it again?
Okay, anyway, so this is, I will talk about this one later as well, because today I am not planning to do this one. So it says actually, and whenever you are talking about that product topology, that's mean any open set will be of the form, any basis open set, any basis elements will be of the form, say xi equal to some uy for now let u equal to u1 cross u2 cross u3 in this way. Then u is a basis element in this product topology if ui equal to xi for all except finitely many. Okay, that's mean if you take any u where u1 cross u2 cross u3 all of this kind of thing, then u will be a basis element of the product topology if ui equal to xi, that is the whole space for all except finitely many. That's mean only finitely elements of in this product will be the open sets in the open sets, and remaining elements will be the whole space. Okay, and in the box topology we will not have any restriction. That's mean any open set will be an basis elements of this. Any this kind of product, any product will be a basis element of box topology. For an example, take R, say it is called R omega, defined by this R cross R cross R. This one. Now if you take U equal to say 0, 1, open interval. This one, this is open in box topology, but not open in product topology. Okay, so U is not open in product topology. Now what will be the open set in product topology? Now this type of element, so 0, 1, say 1R, say 0, 1, 0, 1, and say remaining all are R. Now this is an open set in product topology. Product topology as well as box topology. Okay, or it is same that basis element, and it is not open, or you can say it is not open, you can say. Now here it is open means it is basis element. Okay, so if you take say one in open set, any open set, arbitrary open set, and if you take product of this one, then it will be basis element or open set in box topology, but that will be not be an open set in the product topology. Why? Because in the product topology, if a set will be basis element or that basis open set, if and only if only finitely number of component will be the proper sets, and remaining all will be just whole set. Is
Yes,
that,
yes,
that
yes.
okay? Good.
Box topology finer than product topology in this case?
Right, right, of course. Because box topology has no restriction. You can take any kind of product of open set, that will be an open set. But for the product topology, we have restrictions. That's mean box topology is finer. That's mean larger. Okay. But in other subject, when you say about, say, you have some countable product, in fact, you may have infinite product as well, any arbitrary product. Then when they say product topology on that one, then they always mean this one. So box topology, the concept of box topology, it is very, you can say very specified concept, and it is only important in this our course only. Okay, but in general context, this one will be important. You will see why this product topology is important and why people defining box topology. You will see lots of things. So there will be many things which holds for the product topology, but not for the box topology. Okay, so there will be one chapter on this. So I will talk on this later. But it is good that you asked this one. So now you have rough idea about the box topology and product topology. Okay, now we have projection maps. Now projection maps is very simple concept. Now say you have x1 and say say X and Y, B2 topological space. Now projection map means it is a map from X cross Y to X, pi 1, 1, and another is pi 2, which is X cross Y to Y. So it is the one means first component, two means position on the second component. Now how it is defined? It is defined xy equal to just x, and it is defined pi 2 x comma y. It is just y. Okay, then obviously you can check that pi 1 and pi 2 are onto map, right? And it is also they are also continuous. Why continuous? Can you check that it is continuous?
Sequential criteria.
No. Do not use any sequential criteria now, because now we have topology. Okay,
Okay.
so things will not be true for the sequential criteria. When you say continuous, just inverse image of open set is open. That's all. When we have space R or Rn, something like that, that has been matrix space, then only you can talk about a sequence or all of these things. Okay.
Here pi 1 inverse, sir, here pi 1 inverse U equals to U cross Y.
Right. So now we are done. Now if this is open in X, then this is open in X cross Y. So therefore any inverse image of open set is open, and similarly pi 2 as well. Right? Now that is one interesting theorem actually. You can just think of this one, why this is true. Now if you get that collection, say pi 1 inverse U, where U belongs to say tau 1, union pi 2 inverse V, where V belongs to tau 2, forms a subbasis for the product topology. Can you see that? Can you see the proof of this? The proof is simple actually, just one line answer. Yes. Now you people have lots of doubt on subbasis, right? Now just prove it that this is a subbasis for the product topology.
Because pi 1 inverse U intersection pi 2 inverse V is U cross V.
Right. So it is done. Because take what is the basis element. Now any basis element of product topology is what? U cross V, where U is in open in X and V is in open in Y. Open in X, open in Y, right? Now this one actually, or you can write it is as U cross Y intersection X cross V, and that is pi 1 inverse U intersection pi 2 inverse V. So we are done. So that's mean any basis elements can be written as intersection of basis element, sub-basis elements. So therefore, this sets forms a sub-basis for the product topology on X cross Y. Okay. Fine. Now we define another one, that is subspace topology. So what is subspace topology? Now let X tau be a topological.
Sir,
Yes.
can you please get on the previous page once, please?
What tau do you have?
Sir, I had a small doubt. How do we say that the inverse image of U is going to be open if U is open?
Because pi1 inverse U, that is U cross Y.
Okay, yes, sir, got it. So,
Okay. So once I erase, I cannot go to that page. Okay. Now let this be a topological space. Okay. And let Y any subset of X. Let be a subset of X. Okay. Now this is topological, this is subspace of X. Now we define say tau Y in this way, that U intersection Y such that U belongs to tau. Now can you tell me, now this collection forms a topology or not? Or it forms a basis? Hmm? Tell me. Yes.
सर थिंक टोपोलॉजी फॉर्म करेगा सर.
हाँ, इसलिए मैंने टाउ Y नोटेशन दे दिया. From say topology. It is easy to check actually. Okay. Okay. Now this is a topology. Now what will be the basis? The basis is also simple. Now there is a theorem actually. You can write it as a theorem. So if beta is a basis for the topology on X, then if you take beta dash, say B intersection Y, where B belongs to beta, forms a basis for subspace topology on X or on Y. Now this one, that is this forms a basis, that is very easy to check. To check that beta forms a basis. This is just one line. You can just think about that. Now we will show that this generates the subspace topology. Why? Now let first of all Y belongs to Y. Okay. Now let say U intersection Y be an open set in Y containing Y. So that's mean Y belongs to U intersection Y. And here given that Y belongs to Y only. Right? Now that is subset of U. So that imply Y belongs to U and U is an open set in X. Right? Now by the definition of open set, we know that So there exists basis B, basis element B from beta such that X belongs to B subset of U. Now that implies X belongs to B intersection Y subset of U intersection Y as X belongs to Y. Oh, I have taken Y, sorry. Okay, so we are done. So that implies beta dash forms a basis for the subspace topology on Y. Okay. Okay, is that fine? Now we can compare. Now suppose, see, if you have two topological space X and Y, you first take product topology and then take subspace. Okay, and what you can take first subspace and then take the product topology. Now both are both same. So that's mean what I am saying. So first of all, so let X and Y be two topological space and A subset of X and B subset of Y. Okay. Now let tau equal to the product topology on A cross B. Okay. Where A subset of X has subspace topology and B subset of Y has subspace topology. Okay, and say tau dash equal to subspace topology on A cross B. It is subset of X cross Y, where X cross Y has product topology. Now can you say that tau equal to tau dash? So what you do, you have two topological space X and Y, and you have two, that is subset A subset of X and B subset of Y. Now first you take a subspace topology on A and subspace topology on B, and then take the product topology on A cross B. So this is one way, and another way, you first take product topology on X cross Y and then take subspace topology. Okay, then both topology are same or different.
Sir, need not be same.
Okay, first let's see about the basis. Now say this is the basis element for this and this is the basis element for this. Now tell me what is the basis element for beta? What will be the elements of beta? That's mean the basis elements for tau. So that is that product topology of A cross B, where A is a subspace of A has subspace topology and B has subspace topology, right? So that's mean what will be the open sets?
So U intersection A cross V intersection B, where U will be open in X and V will be open in Y.
Right. So where U is open in X and V is open in Y. Right? And what is the element of beta dash? Tell me again. What is that?
So W intersection A cross B, where W is open in X cross Y.
But right, but we need that basis element, right? But we know that product element of what is the product element of the basis elements?
Cross V intersection.
Right. So we can just take U cross V intersection A cross B, where U is open in X and V is open in Y. Right? Now see that these two are actually same. Now U cross V intersection A cross B is same as U intersection A cross B intersection B. So these two are the same element. So tau equal to tau dash. Okay. See what are the open elements in U? What are the open sets in X cross Y? We know that open sets in X cross Y, sorry, basis elements of the X cross Y is U cross V, right? U cross V is the basis element for X cross Y. And when we are taking subspace, then we are just intersecting with A cross B. Is that fine? Yes or no? Say something. Yes or no? Why you are keeping silence? Yes. Okay. I assume that it is yes. Now tell me, you have say I equal to say 0, 1. Okay. Now again, this is the same thing. Now you have dictionary order. So dictionary order on R2, right? We know we have dictionary order on R2, and we have dictionary order on I2 as well. I2 means that unit square. 1 cross 0, 1 cross 1. So this one. Okay. Now what about this? So dictionary order topology on I2. What about this and this one? That is subspace on I2 of dictionary order topology on R2. Now are they equal? Did you get what I'm saying? First you take dictionary order topology in R2 and you take then subspace topology on R2, I2. That's mean take their intersection and directly take the dictionary order topology on I2. Are they same or different? Yes.
I think no.
No, sir.
Okay, so can you give example? Can you try to give? It is no. Good. Because if you take this one, say this one actually, say this half cross say half comma half cross 1. Now if you take this is open in,
We can construct a set.
this is open in this, but not open in this one. Okay, but why this is open in this one? Because this can be written as half cross half comma half cross say 3 by 2. Okay, and then take intersect with I2. It is same as this one, right? And this is open in the dictionary order topology on R2. Now it is open in the dictionary topology on R2 and then take subspace, then intersection of this one. So we get this. So therefore this is open in this. But why this is not open in the, this is not open in one? Why this set is not open in the dictionary order topology on I2? Because of this point. But that half cross 1 belongs to this set, right? But any open set containing this must contain points A cross B where A is bigger than half. That's mean if you take these points here and if you want to find it open interval containing this point, then it will be something kind of this to say this. It will be this kind of dictionary order and it will stop here.
Sir, if I had been open interval 0, 1, then they would have been same, no?
In that case that will be same.
Okay.
But this is has a special name. This is called your, now this type of set is called actually ordered square. Ordered square. And also denoted by this I to 0. Not 0, I to O. O means ordered square. Now note that here I should mention, now say this is your ordered square. That's when it is 0, 0, 1, 0, 0, 1, 1, 1. Now suppose this is a point, say A cross B. Now say this is a point, C cross D. C cross D. Now can you tell me what is the, can you draw what will be the open set containing, what will be this open set A cross B, comma C cross D? What will be this open set? Can we draw this? Is this open set in the dictionary topology? No, you should not have done this mistake, right? Because any elements is more than 2 will be going to this direction, and then somewhere it moves to very close to this one. It is this. Then again it goes to this. Then again it moves to this direction. Then this. Now when we move to this direction, okay, we do not know which is the next one. Sorry, I just missed one part. I should not came back. Because of the pen I missed that one. Okay. What is? First you have this, so go move with this direction. Okay. Now after this, we have to stop here, right? And what will be the next element? Next element will be somewhere here, right? So again we move to this direction. Then what will be the next element? Now again it is in the lower. Now again we move to this direction. So we always go to from lower to upper, and whenever you go, when you stop here, and then we have to go back to this. And we will go back in this way infinitely many times. And then finally we will reach to this. So this is my actually this open interval. There is no gap. Okay, so there is no gap. Because if you take any point, say this point, what is this point? This point is my A cross 1. Now what is the next point of A cross 1? It is kind of, see, you cannot say that what is the next element here. You cannot say, right? But you can compare. So if you take any next element from this, then any element, say if you take A cross 1 and if you say B cross 0, and if A less than B, then what is the relation between these two? This. Right? If you take any element which is any point which is just bigger than A, and if you take that cross 0, then that will be bigger than this. Okay. For an example, now if you have say this and say this, say this is my X, say this is my Y. Now tell me X is bigger or Y is bigger?
Y.
Y, right? Because of this relation. Good. Okay, we can stop here, and in that one, which I just uploaded now, the lecture 3, you can just go through this lecture 3. Where it is? Okay. Now everything I have written here, these two. Okay. Now go through that. Now remember that. So now read this one. That is, you know this part. So I have written. I did not mention here. What is the definition of closed set? What is the definition of interior set? What is the definition of limit point? You know from your calculus course, right? Even you have read from your BSc as well. Just go through that one. So I will not talk about this. That closed set, closure, you know, right? What is a closed set? If its complement is open. What is a closure? Closure means that smallest closed set containing A. What is interior? That is the greatest, that is that largest open set contained in A, right? And what is the interior point? Now if you have interior, if you take any point of that interior, that point will be an interior point. And what is a limit point? That limit point does not depend on the set A, right? So we can take for a uh, to define limit point of a set A, we can take a point X from the outside, and that X will said to be open limit point if every neighborhood of X intersects A other than X itself. Therefore, A intersection U minus X is non-empty. And this is true for any open set U containing X, right? You know all of this definition. Okay, now just read this part and we will meet. We will meet in the next lecture. And also try the tutorial problems as well. I have also uploaded a tutorial too. This one. You just try to solve this one as well. Now you can go through this one. Only you can leave that house drop part, which I will talk about in the next lecture. But you know what is the closure. You know what is this. You know everything actually. You know the limit point. Okay. Now try that tutorial sheet 2 as well. And in the next lecture, I will talk about that house drop and continuous function and maybe few more on which is the next that box topology and product topology.